Hi, everyone. My name is Tomar Yavetz. I'm a graduate student at Columbia. I am excited to tell you about splitting stellar streams around separatrices and a lot of S's. I neglected to write here, but I should mention this is work done in collaboration with Catherine Johnston, my advisor, as well as a few other folks in this room, Adrian Price-Whelan, Sarah Pearson, Martin Weinberg, through various phases of this work. The broad idea of this talk is to try to convince you. So first of all, I will show you a mechanism that we've discovered to take what was one stream and split it into multiple components, basically bifurcate it and give it several different elements, essentially turning one stream into two or more. We do that by putting these streams in potentials that are slightly deformed, so not spherical potentials, but potentials that are either squashed or even triaxial. And the overall goal here is to convince you that by reversing this process, if we see streams that have interesting features like bifurcations, we can then reverse the process and learn what the actual shape of our dark matter halo is. So let me start with a general overview of what a stellar stream is. A well-behaved stellar stream, like the one I've modeled here, looks very nice. It's a long, thin structure that more or less follows the orbit of the progenitor object, so a globular cluster or a dwarf galaxy, slightly misaligned with the orbit that's expected, and it looks basically like a nice, long, thin tracer of the orbit. And this is one of the reasons stellar streams are super useful in galactic dynamics, because it's really nice to be able to see orbits even though we only have a snapshot of our galaxy. But not all streams are well behaved like the one I just showed, and that makes things interesting. So here are a few examples of stellar streams that we know of that are misbehaved, that do not behave the way we necessarily expect. So one of the first ones that we know about was Sagittarius, which has this nice bifurcation here. So again, a stream that it should have been one long thin filament, but actually it looks like two. More recently, we've found a few other examples. So this is Jalum, which has a nice long thin component, as well as a thicker component here. This is by Benatza et al. Just from 2 years ago. Jalum is even more interesting because it appears very near to Indus in terms of its orbital parameters. So perhaps Jalum is part of a larger stream and was somehow split apart or broken off from Indus by some interesting mechanism, hint, hint. And finally, I'd be remiss not to mention PAL5, which sort of started this whole investigation, thanks to Sarah Pearson a couple of years ago. And this is a more recent image of PAL5, again, from a paper by Anna Benatza, where you see this fanned out end of one of the arms is more fanned out than the other. And the question is, why do these streams not behave the way we necessarily expect them to? So I'm going to do two things. I'm going to first talk a little bit about orbits, individual orbits, and then I'm going to try to relate that back to streams and why we expect these streams to fall apart or really follow trajectories that don't adhere to the typical one-dimensional single filament that I showed before. So we need to start talking about fundamental frequencies. Frequencies, somebody mentioned earlier, if you look in action angle space, then frequencies are the partial derivative of the Hamiltonian with respect to a given action. But easier to think of them as just the way that an orbit evolves in a potential. So if we take a simple orbit in a spherical potential, two frequencies that are very easy to think about and important to think about are the azimuthal frequency, so how the particle moves around the galaxy, and the radial frequency, how it moves in and out with respect to the center. And if those two frequencies are some irrational factor of each other, this orbit will evolve in this nice rosette pattern, eventually filling out the entire donut, the entire torus that is available to this orbit in terms of its energy, because again, these frequencies are some irrational ratio with each other. So this is kind of a typical regular orbit, the way we expect most orbits to look, especially in a spherical potential. What happens when those frequencies are a rational ratio of each other? So this is an example of a 3 to 2 ratio between the azimuthal and the radial frequency, and the star basically just repeats its motion because it closes in on itself. Special orbits, closed orbit. I think the best way to refer to this orbit is it's a commensurable orbit because its frequencies are commensurable with each other. But often you'll hear this referred to as a resonant orbit because we have a resonance between two of the frequencies. These orbits are fun, they look nice, but in this spherical case, it's not a particularly interesting orbit because one of these frequencies relates to a physical difference in the characteristics of the orbit. The radial frequency tells you how close the star is to the potential, and that actually matters. But the azimuthal frequency is essentially boring because it doesn't really matter where the star is around the potential. It always feels the same force, the same acceleration, regardless of its angle, again, in this spherical case. Things get much more interesting when the two frequencies relate to two different quantities that change with respect to each other. So now we're going to take this potential and we're going to squash it. We're going to make it an oblate axisymmetric potential. And we're going to look at the motion in R and in Z of three different orbits. And we'll see, we'll see two very different behaviors here. This is, again, the behavior of an orbit where the frequencies are just some random irrational number ratio with each other. It fills this entire space in the RZ plane. These orbits are doing something very interesting. They're not filling the space that's available to them, and that is because these are resonant orbits. This one in particular is very close to an orbit that parents an orbit family because the radial frequency and the vertical frequency in this case are commensurable with each other, which means that every time the star oscillates up and down, it oscillates in and out, and it feels a stronger tug at different points in its orbit because the Z axis we're talking about an oblate potential. It's feeling a different force or acceleration depending on where it is in Z, and the same is true for R. So here you get kind of a resonant tug that deforms the shape of the orbit, and in fact, it captures orbits that are nearby and forces them to also take this sort of banana-like structure. So we call this an orbit family because here we have a bunch of orbits nearby each other that are characterized by this same kind of orbital frequency ratio. And as a result, they do not fill the entire space that's available to them like this one does. Why is this interesting? When we look at a surface of section, so we're going to just take those same three orbits and we're going to evolve them and we're going to record the points at which they cross the Z-axis. When we look at those same three orbits, we'll notice that this one fills up this entire circular shape here in the surface of section, and you can see each time it's crossing the Z-axis, leaving a point, whereas these two are staying constrained up here. And it's a great way to basically see that the area available to this orbit is not maximized by these. They never reach below the Z-axis here in this plot, which means these orbits are just fundamentally different from each other. So far, orbits. Now let's talk about what happens when we put streams or collections of orbits in these surfaces of section. So really what I want you to imagine now is instead of a single contour in this surface of section, we're going to take a stream, which is basically a progenitor which is leaking particles on nearby orbits next to each other. So first we'll start with a stream on a regular orbit, and that's going to mean we're going to have a bunch of particles on contours very near each other here in this plot. And we're going to look at this, we're going to look at the, I should take a second to explain what you're going to see here. In this plot, you're going to see the evolution of the stream in real space. In this plot, you're going to see the surface of section corresponding to that stream. Here you're going to see two different colors. These are the leading and the trailing arms, and I've also marked the progenitor's orbit. And those same colors are matched here with the plus sign marking the actual location of the progenitor in the surface of section. And let's go. This stream is, again, this is a regular stream. It's going to evolve more or less as we expect. So when we look here, we're going to get that typical spreading in one dimension, more or less along the direction of the orbit. And here you're going to see that the stream is slowly phase mixing in this surface of section. The particles that were leaked earlier will appear further and further away from the progenitor, which is again moving along here. If we give this enough time, it will completely phase mix. It will fill the entire kind of surface of section around, And at that point, we'll also see the streams close in on itself, wrap around once. And again, this is the expected behavior. Now comes the fun part. What happens when the stream evolves near one of these resonant areas, near this resonant island of orbits that have these commensurable frequencies? What you're going to notice is that some of the particles are leaked into those special orbits and don't access the full surface of section, and as a result, interesting things are going to happen in real space as well. So let's let this evolve a little bit. Let it go for a gigayear here. So far, everything is as normal. The appearance here is also more or less the same. You've got a leading and trailing arm. I'm going to pause it here. Again, so far so good. But what you're going to notice now is that some of these red particles are going to get stuck up here, and you're going to essentially get two different clusterings, one up here and one down here. More. Look right now, we've gotten there. Notice here you've got a clustering up here, you've got a clustering down here. They've separated away from each other, and that translates into this little section of the stream up here that's completely separated from the rest. If you keep tracking that, you'll see actually, if you look here, you'll actually see it looks like there's a second red stream appearing in this plot. We've taken the stream, we've bifurcated it around this boundary between the orbit families. We call that boundary the separatrix. It will continue to evolve. Bottom line, though, is we have, through just deforming the overall global shape of the potential, we can take a stream and we can bifurcate it into two different parts. That may help us explain something like Sagittarius. We've actually seen, we've evolved similar objects to Sagittarius to get a bifurcation. It also may help explain objects like Jalen, which is pulled apart from its other stream. And again, successfully fitting these things and showing that we can recreate these things just from the shape of the potential is a great way of diagnosing and characterizing its overall shape. I'll leave up my overall conclusions.
Thanks for the fun talk. You mentioned that you had something that looked a little bit like Sagittarius. Do you have any idea what the resonance is in that case that's causing your Sagittarius-like simulation to bifurcate?
The best I've done is one where I take the halo itself and I squash it along the same axis as the disk to about a 0.6 ratio in density. And in that case, I get it on the it's a resonance in R and Z. So it's either the 1-to-1 or the 2-to-1. And I'm blanking now on which one it is, but it's one of the kind of primary resonances in R and Z.
Is that like a Q of 0.6?
It is a Q of 0.6 in density. Okay. So it's about 0.8 in potential.
Cool.
0.7.
Cool.
So I love this talk, by the way. When I think about stream splitting, the example that immediately comes to mind is Atlas Alico Uma. So this is a stream that S5 has done a lot of work characterizing, and basically, if you look in like proper motions and kinematics, it looks like one coherent stream along the sky, but spatially, Atlas is offset by Alico Uma just slightly. Do you think that this could be a way to do that, or?
Without having tried Atlas Alico Uma, which is on my list, by the way, I can't say for sure. Certainly, we because we're kind of just playing in the parameter space of squashing the halo any way we want right now to do these things, we have a lot of freedom. Of course, the challenge is to make it work with all the other constraints we have for our halo, so I can't guarantee that it's going to work. But I will say, just from squashing things on an axis, just from one axis, we have a considerable amount of freedom because there are several things at play here, both the location of the progenitor with respect to the resonance, the size of the resonance. So is it fully enclosed? Do you just leak a few particles in there? Where are you, which arm is leaking into the resonance? Is it capturing just one arm or both arms? So you get a whole slew of different types of bifurcations. And I would say probably, but we need to check it out.
Thanks for the awesome talk. One quick point that you should totally try out a prolate tilted squashing. And the second point was, can you also get sharp bifurcations like GD1, where we think it could be due to like a dark matter particle going through?
Great question, and one that Adrian posed a while ago to me. It's harder because this is something that's more global on the stream. It doesn't hit a specific point of it that much. What I will say that we can get is multiple. So as it's evolving in the space in the surface of section, it's going to hit this. It's going to every now and then it's going to encounter one of these resonant islands along its trajectory. So you can get multiple bifurcations along different points of the stream. But finding kind of a sharp gap with an associated bifurcation, I haven't succeeded to do yet, and I think it's probably a less local effect than that than a subhalo would cause. Few, exactly.
Monica. Sort of answered it. I was just wondering whether you get bifurcations in both streams with similar, both leading and trailing arms with similar separations.
It totally depends. So here's an example. This is a triaxial halo, and I'm looking in frequency space. What you see here is the orientation of the stream in frequency space, and here are resonances, these overdensities in the dots here. So it really depends on the orientation of this with respect to the resonance it's hitting. So the resonance can cross this way and grab both arms. It can just slice off one of the arms. We have flexibility to do that in multiple ways.
Talk. I was wondering that instead of squashing the halo that you have done here, could you have similar bifurcations but just having a disk and a halo?
Yes, so great question. The first example I showed, most of the simulations I showed are from like a disk-like potential and at a radius that's much more likely to be like a solar neighborhood-like orbit. So, we're thinking of a stream that's like at 10 kiloparsecs or so. That's much smaller. And then I talked about Sagittarius, which is obviously much further away, which requires squashing the halo. But until then, all of it was with like a disk-like, a prominent disk-like potential.
Okay, so could you like distinguish between a disk and a halo, and just a squashed halo without the disk?
That's a great question. Yes, and I think the main key there is where is the stream? If it's a stream that's nearby where the potential would be dominated by the disk, it's the disk that would matter. But for something like Sagittarius, is too far away to feel the squashing from the disk, and you really need to squash the halo to get these effects. I mean, it feels a little bit, but to get a strong resonance that does this, you actually need to squash the halo.
Nice.